So in this class, we will talk about one of the very important reaction about carbonyl functional group, which is called nucleophilic addition reaction to carbonyl carbon. And this reaction is one of the core reaction for organic chemistry because we have lots of molecules that have carbonyl groups present. Anyway, so for the carbonyl group, CO double bond, due to the electronegativity of the oxygen, we have a partial positive charge on the carbon. So the carbon will be an electrophile. It will react with a nucleophile. So nucleophile can attack on the carbonyl carbon and break the CO double bond. The electrons goes to the oxygen to form the alkoxide. And after protonation on the oxygen, it gives alcohol as the final product. So this reaction can provide alcohol as the final product with different nucleophiles, different functionality attached to the carbon with the OH. The nucleophiles could be based on carbon, oxygen, or nitrogen. So we will start with carbon nucleophiles first. And the first reaction is the one that you have learned from last chapter, Grignard reaction. The Grignard reagent is an organometallic compound. So the carbon has the partial negative charge, which is a nucleophile. So the carbon of the Grignard reagent can attack on the carbonyl carbon, nucleophilic addition. So it gives the alkoxide. It forms a new carbon-carbon bond and gives the alkoxide, the O-. After protonation, we get an alcohol as the final product. Grignard reaction is one of the most important reaction in organic chemistry because it has the universal way to make alcohols. It can make pretty much any alcohol. And it forms a new carbon-carbon bond, which is our ultimate goal to build bigger molecules from smaller ones. The second reaction with oxnolithium reagent. This is essentially the same type of reaction as Grignard reaction. Oxnolithium reagent has a carbanion that can be the nucleophile to attack on the carbonyl carbon. So it gives alkoxide first, and then after protonation, alcohol will be the final product. Similarly, it forms carbon-carbon bond. It gives alcohol as the final product. We use Grignard reaction more often because lithium reagents are just sometimes too reactive, so it's hard to control. Okay, so Grignard is less reactive and it works better. The third nucleophiles we will look at is acetylide. So from chapter 7 regarding alkynes, we know that the hydrogen attached to CC triple bond is acidic. The two-carbon alkyne, common name acetylene. When we remove the hydrogen, it gives acetylide ion. We use a strong base, sodium amide, to do that. Acetylide actually is a carbanion, negative charge on carbon. It's a nucleophile, so it can react with the carbonyl carbon in the same way as other carbanions do, like Grignard reagent or the organolithium reagent. So it breaks the CO double bond. Now we have a CC triple bond attached to the carbonyl carbon and a negative charge on the oxygen. After protonation, we get an alcohol. This alcohol has a triple bond attached to the carbon where the alcohol is attached to. So it makes this special type of alcohols. Now I just want to quickly review the use of acetylide. Acetylide is a carbanion, so it can be nucleophiles in different reactions. If we react acetylide with an alkyl halide, an SN2 reaction will take place. So an alkyl group will be attached to the triple bond. This is the alkylation reaction to make alkynes that we have talked about in chapter 7. The second reaction for acetylide is the reaction between the anion and an epoxide. Acetylide can open the epoxide ring to make an alcohol with 2 more carbon atoms than the alkynes. The third reaction is the one we just talked about, nucleophilic addition to the carbonyl, and it makes alkynyl triple bond with alcohol. The next reaction we will look at is called cyanohydrin formation. Here we use cyanide as the nucleophile to attack on CO double bond, carbonyl group. In cyanide ion, the negative charge is on carbon, so it's one form of a carbanion. Same nucleophilic addition reaction. So the cyanide is attached to the carbonyl carbon. After the oxygen is protonated, it gives a compound that has OH and the CN attached to the same carbon. This is called cyanohydrin. Okay, OH and the CN attached to the same carbon, cyanohydrin. So with cyanide as a nucleophile to react with carbonyl, it forms cyanohydrin. We call this cyanohydrin formation. It's a nucleophilic addition of cyanide to carbonyl. The overall result is the addition of HCN to the carbonyl. Okay, CN to the carbonyl carbon, H to the carbonyl oxygen. We cannot use HCN, hydrogen cyanide, for the direct addition. Why? HCN is a weak acid, so it does not dissociate very much in solution. And more importantly, you probably heard of this, HCN is very toxic. You don't want to use it in lab. All right? So the source of the cyanide ion is going to be from the salt, potassium cyanide or sodium cyanide. This reaction also gives new carbon-carbon bond. So it adds 1 more carbon from the cyanide to the existing carbonyl containing compound. And the cyanide group can be transformed to other functional groups. For example, cyanide group can be hydrolyzed to carboxylic acid, and the cyanide group can be reduced to an amine. So here are what I just mentioned. Acidic hydrolysis the CN becomes COOH. Reduction by LAH, CN becomes CH2NH2, and amine. So this will make the formation of cyanohydrin very useful. Say we have benzaldehyde, and the cyanide group react with it to give this cyanohydrin. Now, if we hydrolyze the cyano group here, it gives a carboxylic acid. And on this carboxylic acid, the alpha carbon has an OH group. So it's an alpha hydroxy carboxylic acid. It makes this particular compound with two useful functionalities. If we reduce the cyanohydrin with LAH, now we can get a primary amine. And this product has an OH and NH2 group. It's called an amino alcohol. It's actually a vicinal amino alcohol. NH2 group is on the adjacent carbon as an OH. So that's the application to make a cyanohydrin. We can transform the group to other functionality in organic synthesis.